Okay, today we are learning some more physics because the program we are watching today is called Heat. It's nature and transfer. So we are learning about the nature and transfer of heat. And this is by the Encyclopedia Britannica Films. We are well familiar with them by now. And the publication date was 1958. So I can only imagine this is a program that must have been shown to like a high school class or something. Whoever was learning about thermodynamics during this time, I guess. This seems like high school level material, but I guess let's find out, right? Let's dive in actually. Okay, already we're starting on these pictures of these flames, these burners, which makes me think this might be like this might be like an oil company's like propaganda, you know? Like this might be convincing you to buy like a gas from a gas company or something. Like that's kind of the vibe I'm already getting from this, just based on like the burners that they have for the title page. Heat, Its Nature and Transfer, second edition of Distributing Heat Energy. So this is also a second edition. That's interesting because the yellow we watched was also a second edition. So this is like a revised version of Heat, Its Nature and Transfer. I don't know if that'll come into play at all, but it's definitely interesting that they revised these sorts of things. Okay, produced by Encyclopedia Britannica Films in collaboration with O.W. Eschbach, science degree, Northwestern University, Milan Herzog producer. Interesting. So O.W. Eschbach is I've never even seen this. This is not a PhD. It's a science doctorate, I guess. So we're getting the real thing with this thing. We're not getting a PhD. We're getting a SCD.
Civilization as we know it today would be impossible without the use and control of heat energy.
Civilization as we know it today would be impossible without the control of heat energy. That's true, I guess. That is very true that our use of fossil fuels kind of is like the foundation of like modern civilization. That is very pertinent actually, but I don't know. It's kind of a shame that that's the case, right? I mean, I guess even before fossil fuels, we still used like wood for heat energy. So like, I guess extracting heat energy has kind of always been like a boon of the human race.
This film deals with the nature of heat and how it is transferred from place to place.
The nature of heat and how it is transferred from place to place. Unless just in case the title didn't explain that enough for you. I don't even know what I was watching there for a second. Is this like a blacksmith? They're like pounding this metal? I think these are like glowing hot cylinders of metal or something. Yeah, I mean, I guess molten metal is pretty hot. You know, like I can't really disagree with that.
We may begin our investigation into the nature of heat, oddly enough, with ice.
Oh, I thought we were going to begin with like a gas stove, and I was about to say like this is definitely like sponsored by like GE or something. But I guess if we're starting with ice, then I'll leave that comment aside. But hang on, I do want to make a comment on the knobs on this oven because these look like some actually good knobs. I don't know if this is like a universal experience, but like all the knobs on every single oven or stove I've ever had have always like fallen off. Like they've never worked properly. And like, I don't know, these look like good knobs is all I'm saying.
Ice, like all matter, is made up of very small particles called molecules.
You know, I'm going to pause and make a guess real quick. I'm going to guess that they're going to tell us that the water won't freeze until it's fully below 32 degrees Fahrenheit or whatever Celsius, 0 degrees Celsius, I guess. So I think that always blew my mind is that like the water all has to cool down before even a little bit of it starts to freeze. That's just like, I don't know, that's always blown my mind.
In ice, as in all solids, the molecules vibrate rapidly, much more rapidly than is shown here.
See, these animations are the ones that are the craziest, I think, because there's just so many little dots that all have to be hand animated somehow, you know? Like every single moving dot on screen that we're seeing right now is somebody doing that by hand. I guess this is probably a loop though. It's probably like 4 different frames that are just played on repeat. So it makes it look like it's vibrating, but even still, it's still a lot of thought that has to go into this. And just, you know, every single dot has to be animated still. But yeah, it is a loop, but it's still like a lot of dots.
They vibrate back and forth in about the same place. As we heat the ice, the temperature of the ice rises to 0 centigrade.
Oh, that's interesting. So they're using Celsius, or I guess centigrade, which is the same thing, but it's just interesting that they're not using Fahrenheit. I really would have thought they would have used Fahrenheit. I just I mean, I guess it makes sense for them to use Celsius, obviously. It's just this is an American production, so it's just that's surprising. I wonder if people back then were capable of hearing centigrade and understanding it. Like obviously 0 degrees centigrade is like an obvious one that probably most people know, but like I don't know. I just can't imagine Americans from what 1958 knowing Celsius that well because we don't even know it today, you know?
Even though more heat is applied, the thermometer still remains at 0 centigrade, while the ice at the left melts.
Oh, this is a cool animation. So you get to see like the solid, stable atoms and then like the melted liquid atoms. This is, yeah, just cool animations all around, really. It's just like this is the same exact animation I would make if I had to explain this. You know, like there is no better way, visually at least, to communicate that these are all made up of little molecules that are all moving to different degrees. You know, like this visual has not aged a bit since this was made. Like this is still the perfect visual for the lesson that we're trying to teach right here.
Its molecules vibrate faster and faster until they break away.
Oh, and the little pieces of ice also melting. So this is actually a really complex animation. If you have pieces that are disappearing while other pieces are moving, while you have looped animations on top, this is just so much is going on here that like you can't even see. It's just, I feel like I'm uniquely qualified to appreciate animations like this because I've had to make them like this. But it's just like, there's so much more work that's going into this that we're not seeing.
To move about even more rapidly as water. By now, most of the ice has melted, but the temperature is still at 0. Only when all the ice has become water does the temperature begin to rise.
Only once everything has melted does the temperature increase at all, which is just so bizarre to me. You know, you would think that it would be able to increase, but because there's ice in it, it's thermodynamics, I guess.
Just as heat first caused the ice molecules to vibrate faster, so continued heating causes the water molecules to move with ever-increasing speed.
Yeah, we have a few little audio blips and glubs here and there, but I don't think we're losing any information, thankfully.
Again, some of them will break away. As molecules...
Oh, there's a bit of an audio glub there that I think we did lose some information on, actually. So we're going through a little bit of a rough patch here in the editing part, but like... I don't think we've lost that much important information still.
When the water temperature reaches 100 degrees centigrade, the water begins to boil. The temperature about 100 degrees until all the water has turned to steam.
Yeah, like the temperature won't increase past 100 until it's all steam, which is just, I don't know, it's crazy because the steam obviously is hotter than 100, so it's just, you would think that the water could exceed that temperature, but then you realize that the laws of physics tell you that they have to change from water to vapor at that temperature, and salinity and whatever pressure.
So we have seen that heat is a form of energy caused by the motion of molecules.
All right, so that's what we're trying to establish, that heat is a form of energy transferred by the movement of molecules. That is very, very correct, obviously, but like very important to understand if you were to understand any other thing about thermodynamics, is that it's all conveyed through moving particles or moving molecules.
The faster the molecules move, the more heat energy there is in the substance. Heat energy can be transferred from one substance to another. The heat from...
Hang on, there's multiple ways to transfer heat. Can I come up with them before this program? So there's convection, there's conduction, there's radiation. I think those are the big three. I don't know if there's one more. I think there might be one more, but I think those are the big three forms of heat transfer: convection, conduction, and radiation. That's what I'm going with. Convection, conduction, radiation. Those are the three forms of heat transfer. There might be more, but I'm going to pat myself on the back if we hear all those.
From the flame is transferred to the dish, and from it to the water.
Hang on. Can I guess that? Hang on. So the heat from the flame is transferred to the dish through radiation, I think. And then the heat from the dish is transferred to the water through conduction because they're in direct contact with one another. And then the heat within the water is circulated through convection. So it's all three heat transfer methods in one. That's actually pretty cool.
The fact that heat is a form of energy which can be transferred from one material to another is the basis of all heating systems, whether in industry or in the home.
Heat can be transferred from one thing to another. Yeah, that makes sense. You know, and there's not really going to be much factual argument from me in this video, I don't think.
We shall demonstrate how three fuels, coal, oil, and gas, are burned in the three basic heating systems which use hot air, hot water, and steam for heating.
Coal, oil, and gas. So I guess those are all different.
Let's start with coal.
Okay, so this is interesting. So we're actually getting to see how heat is made using coal specifically. That's like interesting. That's very interesting.
In any fuel-burning furnace.
Oh man, look at this. Another fantastic animation. It's just like, I feel like no one appreciates these anymore. Again, it's another loop, obviously, but like even still, it's impressive. Like this one shot is straight out of a real engineering video. Like tell me differently, right? Like we have the whole diagram, we have the lines and all, like this is straight up real engineering I'm watching right now. The only difference, I guess, is real engineering. Brian would never make a video about heat and heat transfer, you know, like that's the only difference. He would never make a video about a coal burning stove or whatever. But back then, that's exactly what they would make these sorts of videos about. So like that, again, we're getting to see the preservation of this old form, this old interesting technology called a coal burning oven.
Air is as important as the fuel itself. For instance, coal will not burn unless there is a sufficient supply of oxygen from the air. This furnace burns fuel oil. First, the oil is atomized into fine...
Okay, cool. We're getting a diagram for each of these different fuel types. That's cool.
Atomized into fine drops by the sprayer shown here at the right. The fine mist of oil, mixed with air, burns readily. Again, it's necessary to have an air inlet because oil will not burn without the oxygen from the air.
I think it's safe to say nothing will burn without oxygen from the air. I don't know if we need to keep repeating that. Maybe I'm wrong about that, but I'm pretty sure you need oxygen for flames. Or some other sort of, you know, fuel source.
Another type of furnace burns gas, either natural gas or coal gas.
Natural gas or coal gas? You know, I've never really heard of coal gas before. That might be like an old-timey thing as well. Coal gas. I don't know. That's interesting though. Can somebody explain to me coal gas in the comments? I'm curious.
Air is allowed to enter through a hole in the side of the gas pipe and mix with the gas. Here again, the oxygen of the air is an essential part of the burning of the fuel.
Yeah, again, we don't really need to know that. So all of these seem to work pretty much exactly the same. They intake air, they use that air to fuel a fire, and then they take that warm air out. Like that's, I don't even know if we needed all those diagrams, to be honest.
Wood is the oldest type of fuel. A century or two ago, the fireplace was the chief method for heating the home. The heat energy of the burning wood was transferred to the air in the room. Most homes today use central heating systems, which avoid dirt and smoke in the house.
That's so funny because this is exactly what my house still looks like. I still have all these metal heating ducts all over the basement roof. I guess there is no better way of directing air than a big duct. It's just like, I guess some things don't change. We have hit the peak duct design, you know, like there is no better air duct system that we could have adopted. Like we're looking at it.
First of these is the hot air system, which uses any one of the common fuels, gas, oil, or coal.
You know, I do think it's interesting that they're distinguishing between those different fuels. Again, this is probably like some oil company funding this program to get you to appreciate oil fuel more or something. But like, so I think that's why they're doing this, so that like it'll be like Chevron, you know, providing you with all your coal or whatever the hell, you know, people were selling back then. It's just, it seems very pointed that they're mentioning these different fuel sources.
The firebox is surrounded by a large sheet iron jacket. An air duct enters the enclosed...
Dude, I love the little arrow animation moving too. That's just like a little glass plate that they're moving. Oh, it's so funny.
Space at the bottom. The heat from the firebox...
And this is straight up real engineering right now. Like this is an animation, you get it all. Like this is perfect. This is exactly how this video would be made today too.
Box is transferred to the cold air entering the intake duct at the bottom. since volume 4...
Oh, and there you go. There's the convection. You have the circulating air bringing warmth. This is such a cool diagram, too. This is a lot more fun than I expected to be having watching something called Heat, Its Nature, and Transfer. Like, this is actually interesting for what it's worth.
volume, hot air is lighter than cold air. It rises through the ducts to the rooms above.
So maybe they aren't going to use any of those terms. Maybe I just brought those terms up to make myself feel good. But like in physics class, in like Physics 101, they would drill into your head that this is convection.
In the room itself...
Maybe that's just me. Maybe that's just the class that I took. But like I just have that term ringing in my head as loud as possible. And I'm just like, the only way to get that to stop is to say it out loud.
The hot air also rises and circulates. This circulation of air is called convection.
Oh, they are using the terms. I'm proud of that, and I'm proud I called it too.
Hot water furnaces are often used because they provide a steady heat.
Hot water furnaces. That's interesting. I'm pretty sure that's the same type of furnace I still have.
Because they provide a steady heat.
A steady heat. I wonder why they provide a steady heat and the others don't. I don't know if we're going to get that explanation, but I'm curious.
In the hot water system, there are coils at the top of the firebox through which the water circulates.
Oh, this is cool too. So yeah, you were getting to see the water enter the firebox, and that's how it gets heated and leaves as hot water. That's interesting. I mean, I guess I could have expected that, but like, just to see it displayed like this is cool.
The hot gases from the flame rise up around these coils, and some of the heat is transferred to the water. Water heated in the coils expands. As it expands, it becomes less dense and therefore lighter, rising up through the pipes into the radiators above.
You know, it's so funny because growing up, I did have radiators in my house. I didn't have central air or whatever else people have, forced air, whatever it is. But I did have radiators. So this is kind of actually really interesting to see how radiators work. Because I guess, like, for me, it was always just hot. It felt like hot water. I guess it's just hot air, but it felt like they were just running hot water through the radiators. But I guess... I don't know, it's funny. It's funny learning how my old house works.
The heat energy of the water is transferred to the radiator and is in turn transferred to the air, which circulates through the room by convection.
I feel like radiators are not very common nowadays. I feel like most new houses are built using forced air or some other methods. So it's funny to be learning about radiators in a time where that's probably not even important information anymore.
As in the case of the heated air, this movement of water depends upon convection currents.
Yeah, another pat on the back for convection, for calling that.
In the steam heating furnace, heat is used to change water into steam. Water in the boiler is in direct contact with the wall of the firebox. The boiling water turns...
Yeah, I'm pretty sure this is like exactly the same as the last one. Like it's just, yeah, you're using fire to heat up water. Yeah, you're using fire to heat up water, which produces steam, which causes things to move. You know, like I feel like all of these are going to work exactly the same.
To steam exerts pressure in the radiator.
I would be shocked if there was a heat transfer method that I did not know about illustrated in this program. I'm looking forward to it, but I'm pretty sure we're going to see the same thing one more time for the coal or the oil stove.
Is above. Here, the steam gives up its heat and condenses to water, which returns to the boiler, and the process continues. Once more, we see the body of air carried through the room by convection currents. What causes these convection currents in gases and liquids?
What causes these convection currents in gases and liquids? I know this is not something I was supposed to answer, but I'm going to answer it anyways. I mean, he already mentioned what causes convection currents, but it's because something that is hot is usually less dense, so it rises to the top. Something that's cold usually falls to the bottom. Again, it's all about the moving molecules. That's why we established it at the very beginning of this program. Because if you don't understand the molecules jiggling around determines their heat, then you don't understand like why things go up when they're moving faster and why things go down when they're not moving as much. That's just so foundational that you have to understand the molecules are what make the convection cycle happen.
When heated, the air or water molecules move faster and faster, and so bound farther apart, leaving
Yeah, this is exactly what I was just trying to describe.
fewer molecules in a given volume of air or water. This makes the air and water lighter, and so they rise, causing convection currents. Therefore,
Yeah, it's just the rising and falling of cool and hot air. That's all that really is all convection currents are. And you can have convection currents in water too. You can have hot water rising and then cooling off and then falling, and that's how you get ocean circulation and all that sort of stuff.
convection currents are one means of moving large quantities of heat from one place to another, in water and in air. A second method of transferring heat is by conduction.
Conduction, all right, so we are getting all the terms in. That's cool.
Here is an example of conduction. Heat from the hot end of this iron bar will be gradually transferred through the bar. This transfer takes place because the rapid vibrations of the molecules at the hot end cause the neighboring molecules also to vibrate faster. Heat transferred...
Yeah, this is pretty much just intro to thermodynamics. This could be just like your first day in college, or maybe even first day of high school, really. I took physics in 9th grade in high school. So yeah, the first day of high school, this is probably what I was learning.
To the opposite end of the copper rod is great enough to light a match. All metals are relatively good conductors. Materials such as asbestos, however, are poor conductors.
Asbestos. Wow, this is actually wild asbestos in its own time, you know, like, is this a glove made of asbestos? That's the thing. I don't even know what asbestos looks like, you know, like I've never seen it. I've only ever just heard about it. So it's funny to see a glove just made of asbestos.
Protected by an asbestos glove, the hand can be put...
Like you could just make materials out of asbestos. It was like a textile almost. That's so bizarre. That's just not what I was expecting. I picture like the fluffy cotton candy stuff that we put in homes today. Like that's what's replacing asbestos. So I always imagined asbestos as being this like cotton candy sort of substance, not like a textile canvas sort of material.
Safely into a scorching flame.
That is cool, though. I guess asbestos was used as an insulator, so I guess it makes sense that it's good at insulating this hand from the heat. That's just not something I really would have thought about either, that you would have used asbestos for, like, your firefighting materials.
Poor conductors, such as spun glass, are used to insulate houses. Heat is
spun glass. So this is the asbestos installation, isn't it? Like this, we are watching people install asbestos as installation, I think.
Heat is kept in the house and out of it, partly because...
Don't squeeze those needles into the air. That's all I gotta say.
Glass is a poor conductor, and also because the air between the fibers of spun glass is an even poorer conductor. In some...
Spun glass. That's what they're calling it. Spun glass, which I'm pretty sure is asbestos still. I don't know. I'm not quite sure about that, but I'm pretty sure that's like the same thing.
Older houses, insulation is often blown between the wall spaces to reduce convection currents inside the wall spaces and to reduce transfer of heat.
Maybe not. Maybe this is not asbestos. That might have just been an asbestos glove, because this... Maybe it is, though. I really don't know. This is actually what I was picturing when I thought of asbestos.
Heat by conduction. Besides traveling by convection and conduction, heat also...
Convection, conduction, radiation. That's what we're doing now.
Also travels by radiation.
There you go. There you go. All right. I remembered all of physics. There you go. I'm proud of myself for that.
By means of a reflector, heat from an electric coil can be focused and made to ignite a piece of inflammable material.
Hang on a second. I don't know if that was... I don't know if that was real or not. I feel like I just saw somebody ignite this thing.
Heat from an electric coil can be focused and made to ignite a piece of inflammable material.
Yeah, you can see the little match that the person used to ignite that. That's not being... You're not fooling anyone, all right? Like, I wasn't born just yesterday. What is funny is I have used like a magnifying glass to light things on fire. Obviously, I was a kid who loved spending time outside. So yeah, I totally have lit fires using nothing but like a radiation. I don't know if that's radiation, actually. I don't know. I guess it's a form of radiation. I don't know. It's so funny that they had to fake this whole demonstration, you know? Like, they couldn't actually get it to work. Either they lied and you can't actually light this on fire using a heat cannon, or they just couldn't figure out how to, you know?
Modern cookers and ovens are lined with reflecting materials to take advantage of radiant heat energy.
You know, it's interesting to think that this is like kind of the era that we're first discovering these sorts of lessons. You know, like lining your toaster oven with reflective materials in order to increase the heat radiation. That just seems like a a step in technology that is only just now being taken while we're watching these sorts of videos.
Heat energy from the sun comes to the Earth by radiation. Of the three forms of heat transfer, we know least about radiation.
That's interesting. Is that true still? We know least about radiation? Radiation, to me, seems kind of like the easiest. It's just like, I don't know. I mean, I guess maybe not. I guess it is kind of crazy that heat from the sun affects us here on Earth. You know, like, I guess conduction makes total sense. If something hot is touching something else, that'll also get hot. I feel like convection is the one that fewer people understand. I feel like radiation is more intuitive. Like the heat from a fire you can feel from a distance away, whereas convection, you never see or feel convection. So it's just not as intuitive. So I don't know. I don't know if I agree with that statement, but I am curious to know if that was true back then, if we really did just not know anything about radiation relative to convection and conduction.
The vacuum bottle applies all three of these principles to prevent heat transfer.
The vacuum bottle applies all three. That's interesting. I'm trying to think of how. It doesn't conduct, right? It has the vacuum, so you're not conducting from the outside to the inside, or radiating, I guess. And I don't know how convection plays into it, because you still would get convection inside of it, but you don't get convection within the vacuum chamber between the walls, so you have it insulated that way as well. Okay, I understand now.
There are two walls with a vacuum between them. Since there is almost no air present, little heat is transferred either by convection or conduction from one wall to the other. Since glass is a poor conductor, little heat can travel to the lip of the bottle. And since the glass is silvered like a mirror, most of the radiant heat will be reflected back into the space within the bottle. Thus, liquids can be kept either hot or cold in a vacuum bottle for many hours.
You know, this must have been like really cool technology to them during this time, right? Like they're actually treating this like thermos or canister as like an amazing new achievement by mankind. And it's just so funny because today these sorts of items are kind of regular, commonplace, you know, but back then, like the fact that you could keep a drink hot for hours on end in this container really was an amazing accomplishment of science. Like you are applying your understanding of three different forms of heat transfer in order to avoid it. You know, like this actually does require like high level thinking and a high level of like conceptualization of the problems at hand. You know, like this thermos illustrates our understanding of thermodynamics.
To summarize, heat can be transferred from place to place in three ways: by convection, by conduction.
Wow, I am actually pretty proud of myself for this, for guessing all three. I thought there might have been another way, but I'm proud for having gotten the three primary ways.
And by radiation. There is still much to be learned about heat and its behavior. Because it is one of the principal sources of energy on our Earth, research is concentrating on finding improved methods of producing and controlling heat. Electrodynamic heating and cooling and microwave cooking are results of such research. We can influence...
Again, microwave cooking was just such a new thing for them at this time that they felt like the need to mention it. You know, like that's just so funny, because now I would just never even think about microwaving as like, I don't know, special to this. But I always find this interesting because this has preserved not only the old technology of the time, but it's also preserved people's impressions of the technology. Like you get to see how people talked about microwave ovens before they were commonplace, really. It's just interesting. It's preserving like this sense of like, wow, that like people once had for technology that is now no longer providing that wow for us, you know?
The behavior of molecules inside food without affecting the container. The bacon and eggs were cooked in 90 seconds. The plate remained cold.
Hang on, you're telling me this person cooked bacon and eggs in a microwave oven on a plastic or a paper plate and they're perfectly cooked? I don't know, I kind of doubt that.
Can you tell now how electric current can be used to freeze food? Why
How to freeze food? See, this is interesting because I feel like heat and cold, obviously they go hand in hand, but I feel like it's a lot more complicated to make something cold than it is to make it hot. Oh great, asbestos.
Heating pipes are often wrapped in asbestos. What makes an air conditioner work? Why the builder of a skyscraper or a steel bridge must leave room for the steel to expand?
See, that's something that they didn't touch on at all, how things expand when they heat up. Thermo expansion, I imagine, is what it's called, but like, I don't know, that's another lesson I remember learning in physics that I guess we just get like one throwaway phrase for here. Oh, and there you go, the end. Heat, its nature, and transfer. So that was interesting. I feel like I definitely came to this one a little prepared. I'm glad that I still remember the lessons from my high school physics class, though, even the terms. Like, I'm really proud of myself for that. Like, more so than I should be, honestly. But I don't know. It's just like, I like how I was able to call every single phrase that he was going to say. So that being said, I don't know how much I actually learned from this. You know, like, I like watching these old programs because I feel like there is information that is stored within these that I have not had access to. So that's kind of why I think these things are fun to watch. But this, honestly, I just don't know if there was any new information whatsoever in it. You know, this has really just confirmed that everything that we have now has been around for a very long time. Like radiators and, you know, hot water heaters, like all that sort of stuff has actually been around for a lot longer than I think people imagine, which I guess is interesting. It's just not like a new thing for me to have learned, I guess. I don't know. I don't know how to say that. I do appreciate all the effort they went into to demonstrate the 3 different types of heat transfer, though. Like, they did really do some good animations. They had some good convection animations, some good conduction animation. That one with the steel rod that all the particles were heating up the ones next to them, that was a really good animation, too. There were some real good animations in this, I will say. Like, pretty much the exact animation you would need to convey this information. So good on them for that, for understanding it well enough to explain it to us. This is kind of a dry watch. I hope some of you got something out of it. I know I had fun. It's fun to see how they used to make old programs like this. It was fun to see how they used asbestos too. I guess not fun, but it was interesting. It's interesting because I've only ever heard of asbestos and never actually seen it being used. It's an interesting peek into like a historical material that doesn't really exist anymore. Like, I guess asbestos exists, but no one makes it, you know? Like, it doesn't exist in the same way that it once did, I guess. I feel like my entire audience now understands thermodynamics, which is, I guess, the point. So if you enjoyed watching and would like to help support this channel, there's a link in the description that'll take you over to the Internet Archive. The Internet Archive is where I get all these old programs from. So please, if you want to support me and what I do here, then go over to the Internet Archive and leave them a donation. Besides that, I think we're good to cut to black.